Remember I ate lunch. I hope they have some vegetarian food.
I think so.
Are we on? Okay, good morning, everyone. I'm Eric Person from International Rectifier. I know most of you from last week. My responsibility there is application engineering, and so one of my favorite topics, of course, is talking about FETs. And I've got probably 20, 30 hours of material. Not going to do it all today, of course, but I've tried to select a few of the key topics that I think are the ones that we most often get questions about. Because you've learned from Professor Robbins about device characteristics and so on, but there's a lot of practical application pieces that maybe would be helpful. So I'll talk just a little bit about the structure, the different types of FETs that we have that are industry standard, and why. What you'll notice is a trend here that FETs are becoming more and more application specific. It's no longer that you have a single design and you just scale it for different voltages. Even at each voltage node, you may have quite different characteristics optimized for speed or for conduction, for example. Another big one is understanding and interpreting data sheets, which can be sometimes very confusing or misleading. And included in that is safe operating area, what that means and how to use it. A little bit about thermal modeling, because usually the limits of a device are not actually what it says on the data sheet, but rather how hot it gets and how you can manage that in your design. A little bit about thermal instability, which is a fairly new phenomenon as devices become more and more dense. Just a couple notes on parallel operation, because oftentimes at higher current you need to parallel multiple devices, and now you have to worry about whether they share equally or not. A little bit on new technologies like silicon carbide and gallium nitride. All that in 1 hour or less. Okay, so brief review of MOSFET characteristics. They're a majority carrier device, typically quite a bit faster than minority carrier devices like BJT or IGBTs. However, their conductivity per unit area, because you don't have the conductivity modulation, is quite a bit lower. So there's obviously cost trade-offs, and as you go up in voltage, the size of the equivalent FET becomes a trade-off where maybe where IGBTs become more advantageous at higher and higher voltages. They're gate-driven with a high impedance gate that looks like a nonlinear capacitor. It's very similar to IGBT. The gate drive, even though it's relatively, it's a capacitor, you still need a relatively high peak current to be able to charge and discharge the gate capacitance quickly and make it switch. The safe operating area is quite variable depending on the device technology. FETs usually have no intrinsic short circuit capability. In other words, if you can turn it on, it will draw more than enough current to destroy itself. So you can't rely on the device to self-limit like you can with some IGBTs we talked about last week. FETs all have this, this is the majority of power FETs, which is the vertical DMOS FETs, have an intrinsic body diode, and that typically has pretty poor body diode performance. It depends on the voltage. At 20 or 30, 40 volts, they're actually pretty good. Matter of fact, they can be built with parallel Schottky diode, so you get very good performance. But as you go up to, especially 100 volts and up, the body diode It stores a fair amount of charge and becomes pretty slow. And there are things you can do to speed that up somewhat, but at the cost of conductivity. The package impedance can be quite significant. We're talking about FETs now that are a milliohm or less, and the package itself becomes a huge part of that overall impedance. And as I mentioned, they're becoming pretty application specific. So just a brief review, you've all seen the symbol for an N-channel MOSFET. This is their VI characteristic at various gate voltages. Normally, you're operating either here where it's off, and this is the body diode, so as the voltage becomes positive here and negative here, you reverse conduct with the body diode, and here's the knee voltage. And it's if it's off, you can go all the way up to its breakdown voltage way up here somewhere where it breaks down. And the other way you operate this is when the gate is fully enhanced and you're operating on this region here. Ultimately, it will saturate, but this is usually at a current that will destroy the bond wires and other parts. So normally you can never get up to here. So it's either you're operating here or in this region. Notice that there is third quadrant capability. So if I have positive voltage here, negative here, and currents flowing through the body diode, I can still turn it on, and the channel will conduct, and I get a much lower drop. Commonly, this is called synchronous rectification, and it's very, very frequently used. It helps, instead of a 0.7 volt drop here, you can drop it down to arbitrarily low as your on resistance times current. So this is a kind of a cross section of a device. This is an older, what we call planar style device. This is still commonly used at higher voltages. So the substrate is the silicon. It has a metallization on the back, which is usually aluminum. Then there's epitaxially grown layers on top of that of silicon again. And then there are various diffusions and so on. And then more metallizations and oxide coats and so on to create all these gate structures. So the current flows from the drain down here up to the source regions this way, and you get this region called the drift region here kind of limits the lowest RDS(on) you can get. So the thicker the silicon, the more resistivity you have, and so as you try to go higher and higher in voltage, this becomes a limiting factor. As well, this behaves kind of like a JFET region that I know is in your textbook. So all the action happens right here under the gate, and this is where the applied field kind of throttles the flow of electrons and pinches it off or allows it to flow. The nice feature of these devices is they're spread out. The current flow or the current density is relatively low, so that they work well in the linear region. They can dissipate huge amounts of avalanche current or power, and so they're very stable operating in under adverse conditions. They're considered very rugged devices. But the bad news is, because they're large and spread out, you need a lot of silicon acreage in order to get very high current. So it becomes expensive. So in order to reduce cost, make them more effective use of silicon, about 10, 15 years ago, there was development where the gate, instead of being horizontal across the top, becomes a vertical trench. And these are, it's a classic trench MOSFET, as they're called. You can see in the cross section here, this is the gate that's fabricated in a etched trench on the surface of the silicon. So the big difference here is that now current flows along this gate is now vertical instead of horizontal. So the cell pitch, in other words, the distance between cells becomes much, much smaller, and the overall current density has gone up quite significantly. We're talking factors of 2 or 3 or 4, depending on the technologies. And it also eliminates this JFET resistance that had previously plagued the planar devices. So at low voltages now, I'd say what we call low voltage is, 40 volts and below is considered low. Mid voltage is 60 to about 200 or 300. High voltage is 400 and up. So at low and mid voltage, you'll see almost exclusively trench devices because they're just more cost effective and offer better performance per dollar. At the highest voltages, at 600 and up to more than 1,000 volts, the dominant technology there is what's called super junction. And again, this was a structure that was developed in order to make better use of the silicon area and get very low on resistance. So there are these, essentially, the whole point of this exercise is to reduce voltage gradients so that the silicon can support the high voltage under these very small, in these very small structures. So you essentially have columns alternating of N and P material. The P kind of separates the columns of N, and this is what carries the current. And you can get quite a bit better conductivity, or what we call specific on resistance, which is a measure of resistance per square area. You can do better than what's called the silicon limit here. This is assuming a structure that where the blocking voltage is the same structure that carries current. By doing some of these tricks with these alternating N and P layers, it's not a cheap process, but it does allow very good areal density. And you'll see these commonly made by a number of manufacturers. This is the dominant switch right now in power supplies, for example. The good news is you can get very good conductivity at high voltage. However, the bad news is all these N and P structures store a lot of charge. So the body diode becomes pretty slow. And these are typically used in topologies that only require forward conduction, like boost or, for example, two-switch forward converter. So let's talk a little bit about data sheets. I'll use, this is a typical low or mid voltage data sheet as an example, and hopefully you can read the micro printing here. And I just want to go through a couple of the characteristics and features and common questions that you run into. So the first one you might notice here is that at what we call the cover page gives you the basic characteristics. So what's the breakdown voltage? What's the typical and maximum RDS on? And then there's a couple of numbers here that look pretty alarming. The package limited current and the silicon limited current. It seemed like a pretty large number here, especially for a package this small. I brought a show and tell sample here so you can kind of see this. So compared to my pen, so this is what we call a D squared pack, a D2 pack, based on the old TO220 package. This is like a 30-year-old package or more, wire bonded, and the die is a little bit smaller than this whole area here. And it's been extended so you can get multiple pins in order that you can have more and more wire bonds. So this package right here will carry somewhere in excess of 100 amps for a short time. This one will carry up to like 240 amps, which is quite a bit of current. Again, not for very long, but, and then the packages, of course, get smaller and smaller. You can see what's called the D pack, and I don't have time to go through all of them. But the important thing here is that inside of these packages, there are little, there's wire bonds going to the silicon, and all of them have limits. So I'll explain where these numbers come from in the next couple of slides, but just these, especially this one, is really more of a legacy number that's competitive marketing, right? It's not real. What it says is how much current could the silicon carry if you could actually get that current through it. In other words, and it was temperature limited, and you had an ideal heat sink, like all these what ifs, right? So it's really kind of a useless number. The other ones to keep track of here, gate to source voltage. What are standard gates are plus or minus 20. You don't need the negative usually, it's just 0 to 12 or 0 to 15 is how they're typically driven. But there are low threshold devices that operate fully enhanced at, say, 4.5 volts. There's also Avalanche. This is a measure of if this is used, this should probably be drawn here as a Zener diode. Most FETs have pretty good avalanche characteristics. They can absorb momentary voltage spikes as long as the current's limited and as long as the energy is limited, and I'll cover a little bit more of that in the SOA. Another interesting one to look at is the what's called R theta JC. This is the thermal resistance from junction to case. It's typically given as a max value. Typical could be significantly less than that, but this is a guaranteed maximum. This gives you a good idea of how big the die is, right? If it's an enormous die filling the entire package, it's going to be a low number. Maybe this could be down even as low as 0.25, 0.3. Very small die in a package like this could be 0.8 or 1 degree C per watt. So you move on to the next page. Notice that everything is at 25 degrees C. So that's not very realistic because most times power electronics are operating at higher temperatures if they're dissipating any power. So these are sort of the baseline numbers, and then the graphs later on in the data sheet show you how it varies with temperature. So one of them is what's the RDS on? At 10 volts, typical 1, max 1.3 milliohms. The gate threshold voltage. This is important because if it's too low, you need to be able to keep the device off when you want it off. So becomes tricky in circuits where you have large transients, and you need to be able to guarantee that the gate, under all conditions, large DIDT, poor layout with a lot of inductance and so on, that you can actually keep below this 2.2. Another thing we'll talk about shortly is this is at 25 degrees C. It gets worse at high temperature, right? So the threshold voltage actually goes down. There's an internal gate resistance here, not always specified, but this gives you an idea of how fast you can switch it if you had an ideal gate driver. This is actually a pretty high value. Normally it's going to be in the ohm or sub-ohm range with modern fast FETs. We talk about gate charge. This is a measure. Remember, the gate looks like nonlinear capacitance. When you turn the FET on and off, all of that charge, all that energy is lost, right? I mean, you put it into the gate and you essentially dissipate it through another FET that turns the gate off. So you're basically, when half CV squared F, this charge gets dissipated every cycle. So the larger the gate charge, the more inefficient your gate circuit's going to be. And there's different ways of looking at these charge numbers, and I'll talk about that a little bit more later as well. So getting back to this, how much current can my 400 amp rated FET carry? It's not 400 amps. And I'll show you in the next slide here how we come up with this number and what the realistic number is. And this one is the one that's limited by bond wires. So this one is a real number. However, again, it's at the case temperature 25 degrees C. So unless you have an infinite heat sink, you're not even going to get this much. But you will for short-term overload. So let me show you how we calculate this number of power dissipation. If you start with, so degrees C per watt, this here is R theta, right? So thermal resistance across a barrier is how many degrees C is that device going to rise for each watt of power that I dissipate in it. And if I multiply by that by how many watts I'm dissipating, I get my delta T. So if you rearrange this and just say, well, what's the maximum power I can dissipate? Well, if I know my maximum junction temperature, it's usually either 150 or 175 C. So in this case, we'll say TJ max is 175 degrees C. And I subtract the case temperature, right? So in this case, 25 degrees C ideal. This is the temperature difference across that junction. And this is my thermal resistance. In this case, 0.32 for this example. I come up with 470 watts, which is that's a lot of power. And again, this is assuming you can keep this infinite heat sink at 25 degrees C, which is pretty difficult. But that's where the number comes from. So in real life, you know, your heat sink's going to be probably worst case at 80 or 90 degrees C. And you're not going to want to run it to 175 because reliability is going to be a concern. So maybe you run it at 125, something more reasonable, right? So this number is a theoretical maximum. And the datasheet provides a linear derating factor to adjust for higher temperatures. Let me just show you a real quick example while we're talking about this. So I'll move this out of the way. And this is a power tool motor drive. And what you can see here, this is the trigger switch, and this is some of the couple of the FETs. This is a chopper and diode. This is for driving a brush motor, right? So it's just a one-quadrant switch. So these devices can handle continuous current of about 60, 70 amps and peak currents of up to 180, right? Pretty impressive that the battery pack can even put that out. But that's, and this small little heat sink here is enough to, you know, manage that over short term. And this is like a, you know, half or 3/4 horsepower kind of drive right here. It's pretty impressive how small it is. And a more modern, this is a few years old, more modern manufacturing techniques now are going to smaller packages. This is, it's called a direct FET package. It's a very small, the package itself doesn't have a lot of additional mold compound and wire bonds and all. The die is actually soldered right down to the board, and the can is sort of the cover that goes over it. So this is actually a brushless drive here. So there are 6 switches, each of them comprised of a pair of FETs in parallel. So there's 2, 4, 6, 8, 10, 12. And here are the 3 leads that go off to the motor, and this is the power lead here. And it's a pretty interesting little package the way they do this. You can see that. So here's the controller, and here are the gate drivers. So everything is on this little board that goes into the handle of a drill and powers 500-600 watts. So it's pretty impressive. So back to the temperature effects here. All silicon FETs have this temperature characteristic. It varies a bit by how it's doped, but what this is saying is that at 25 degrees C, I'm at unity, normalized 1. So if my 4.5 milliohm FET is at 25 C, now I heat it up to 125. I'm at nearly double, right? Almost double. So, when you're doing your calculation of how hot's my FET going to get and managing your thermals, you have to worry about what is this coefficient of increase in RDS(on) with temperature. I also mentioned that the gate threshold voltage varies in a bad way. So if I'm at 25 degrees C and I'm at roughly 3¼ volts threshold voltage, when I'm up at very hot, near failure up here at 150 or even 175, and you can see it's dropped by more than a factor of 2. And the problem here is that if your FET, I'll quickly draw a FET here, and I have some kind of a gate driver driving it. All right, this is ground, this is ground. I've got this capacitance from the drain pulling, so as this voltage goes up and down on the drain, it's pulling on the gate, and this is rising voltage when it's supposed to be off, right? So as the FET's turning off, this what's called Miller capacitance, gate to drain capacitance, is trying to do the opposite. It's pulling the gate up. So I need to keep this voltage below the threshold, which could be as low as 1.5 volts. So if my gate voltage bounces like this as a result of the capacitive current injection, if I exceed the threshold, it'll turn back on, and you get additional power dissipation or shoot through, for example. So this is why it's important to keep track of what's the gate threshold at high temperature. So this is what not to do to a FET. Maybe some of you have experienced this in your own labs. So we get parts like this back sometimes for failure analysis, and the customer says, what happened? What went wrong? And you have this charred piece of silicon with plastic bits, and a huge crater, a smoking hole in the middle of this thing. And we have no idea. You have to look at if it's somewhat intact, there is actually quite a bit you can learn from a failure analysis. But so what causes this? Why do FETs blow up? Well, it's really one thing. It's excessive junction temperature, right? From whatever cause. It can be either that excessive current exceeded the conductivity limit, and you dissipated too much power, it got too hot. It could be from switching loss, or a combination of conduction and switching loss, or it could be from avalanche. But there's really only a few things it can be. And the safe operating area is what we'll study a little bit next here, so you can see what those limits are. I know you've probably seen these in your book. Let me explain a little bit about how it's constructed and what it means. So we're taking the example of a 200 volt FET, and the basic, let's call it a curve, but it's a bunch of straight lines on log. So you have drain source voltage on the horizontal axis, and you have drain current on the vertical axis. So we have a breakdown voltage you can't exceed, that's the 200 volts, and then there's some absolute upper current limit. In this case, 1, 2, 3, 4, about 550 amps for a very short time, right? This is just the pulse limit. So if you exceed, if I exceed this voltage limit, what happens? Well, I can do that briefly for avalanche, which is a separate case, not counted on the SOA curve. I really can't go any higher, in current, right? That's an absolute limit, all right? But there's no time. We're missing another dimension here of time. So let's look at, well, actually we're missing the other one is you can't get up into this quadrant. In other words, if I'm able to pump 550 amps through the device, I couldn't be at 1 volt because the RDS on is so large, or not so large, but it's large enough that this line defines what is the RDS on, right? So this is, if you look at every point along this line, the volts divided by current is equal to RDS on, right? So you can't get up here. You can only be in this region. Note that if I multiply out my 500 and whatever amps times 200 volts, you get a lot of power. 100 kilowatts of power at this moment. And this is, within, it's on the edge, but it's still within the SOA. So clearly you can't do that for very long, right? And that's where the next step in building up the SOA curve is to look at what are the time limits. So typically, somewhere up here will be specified for, maybe it's 1 microsecond or 2 or 5 microseconds or something. So it's, and typical switching times, by the way, are usually below that, well below that. So you're talking tens or hundreds of nanoseconds. So a microsecond's even a fairly long time, especially to be at absolute maximum current and voltage. This would be very unusual that you'd actually ever be able to even get here. More commonly, you're well within this SOA. And the SOA contains these lines, and what these represent, each one is a specific power level. So for example here, 20 volts at 400 amps is 8 kW. And every point along this line is 8 kW. So it's saying you can dissipate this power for this long, which is really, it's a measure of energy, right? So these are lines of constant energy. And as the time gets longer, the amount of energy goes up, but the power goes down, right? So then as you approach DC, this is the DC rating of 500 watts, which, as you saw earlier, even that's a pretty optimistic number, right? It's not very realistic. So in any case, when you're figuring out how to operate the device, normally if this is a 200 volt device, you're going to be at half of that, somewhere in the 100 volt range. So you're going to be along this line, and you're probably going to be operating not at this absolute max, but somewhere, in this range. So your locus of points as you turn on and off, you're going to be, operating over here somewhere, and as you switch, you'll be kind of traversing this region, right? And usually only for, maybe 10 or 100 nanoseconds. So these lines, you're well within what we call the safe operating area. It's the only way you can get here to any of these lines is to be halfway turned on, right? In other words, the gate isn't on all the way because I have simultaneously, I'm drawing current, and the voltage isn't zero or near zero, right? So this is what we call linear mode, and it's not how FETs are normally used, but there are fault conditions or other scenarios where you do need to be able to handle that. So that's the point of the SOA curve, is that it's under normal switching conditions, you're operating either here or here, but during switching, especially slow switching or during fault conditions, you could be operating anywhere in here, and you need to make sure that you stay within that. There's also what's called a transient thermal impedance curve. Sounds like a difficult concept, but it really is not. What it says is that at DC steady state for many seconds, this is the datasheet value here of what's my R theta JC of 0.35 or whatever it was. But for shorter and shorter pulses, my effective thermal resistance is quite a bit less. It's just a mathematical way of understanding the pulse energy capability of the device. A really useful tool to look at this is what's called the thermal model, and I'll show you a bit clearer detail here in a second. This is essentially a way to be able to estimate die temperature, and the values you need are given here. I'll get to a better model of that in just a minute. So in the interest of time, I'm going to skip how this is derived and go right to the one of the second key issues that you need to worry about in MOSFETs is what's called thermal instability. So all of these things we've been talking about, how much power they can handle and how much energy they can dissipate, assumes that you have relatively uniform distribution of temperature across the die. That isn't always true. And what you'll notice is that these theoretical SOA that give you a nice straight line, that's true if you do have good sharing. But there's conditions and scenarios where you'll see these cut off. Essentially, it's like a reduced SOA because of something called thermal instability. So what thermal instability is that it's essentially hot spotting, where as long as, if you take the differential of the power generated divided by delta T, essentially, it has to be, if it's greater than the dissipation capability, so this is electrically generated power here, and this is the dissipation capability. If this inequality is greater than 1, then you get hot spotting. So essentially, what it says is that the transient thermal impedance in these regions is unable to handle the amount of power that's being dissipated. Let me show you a clear example here. I think it's easier to see graphically. So if you look at the curve of the transfer curve of the FET, where you have gate source voltage and drain current, and think of it, remember these FETs are made up of thousands of cells. So let's imagine we have, I'll just draw real quickly here, we have 2 adjacent FET cells, right? They're actually tied together. The drains are tied together, the gates are tied together. All right, I'll just draw them quickly this way. So VGS between these two is identical, and I've got current flowing, and let's assume that they're identical and they're sharing. All right. Now here's the curve. So at room temperature, the green curve shows me how much current I get for a given gate source voltage. And the red one shows high temperature. Well, what if I'm right here and these two are, we're turning on and the gate source is coming up, but one cell takes a little bit more current than the other, right? And it gets hotter. So as it gets hotter, what happens? It's going to take more and more current, right? Because this temperature coefficient is positive, that it's taking more drain current as it gets hotter. So if this is the hot one here, it's going to take more and more current at the expense of this one. So you get, imbalance. So as long as the delta ID over delta T is positive, so in this region of up from from here to here, it's potentially unstable. And then above that, now you see it reverses. So now the one that gets hotter takes less current, which is self-equalizing, right? So you end up, in this region, you end up with the likelihood of instability, and as long as the delta ID over delta T is less than 1, then you don't end up with instability. And this is a result of, what I showed you earlier, how you go from planar devices to trench, all in the interest of getting higher current density, higher, more current per unit area. So early devices had very small differences in, delta ID over delta T. But as you get to more modern devices, you can see here, at 5 volts VGS, I could be at 10 amps or at 30 amps or maybe even more, 35 amps. So 3.5 to 1 difference in current between adjacent cells as one gets hotter. So as a result, you see these SOA curves that are no longer just thermally limited, but they have this thermal instability limit as well. So most modern trench FETs you'll see have this kind of a curve, and if they don't, I'd be very suspicious about whether it's real or not. So how is this relevant? Let me show you a quick example of hot swap, which is this is where the FET is used when you have a power supply and it's dead or it's not powered up yet, and you're plugging it into a live bus, and you need to equalize between capacitor banks and connect, right? So during that, usually it's FET operated in the linear region, and you need to absorb energy, and the question is, can it handle it, and what's the TJ going to be? So here again is the thermal ladder network. If you think of this as an electrical analog to actual thermal, this would, for example, be the die, the thermal mass of the die. This is the thermal resistance from the die to its lead frame, and then from the lead frame to the copper on the circuit board, and so on. And the way you work this is you apply. Let's see. Do I have a? Here we go. So the power dissipated by the device is represented by a current. right? So current represents the heat flux power. Capacitance represents essentially charge. So this is the thermal mass. And then the resistors represent thermal resistances. So by using this, if I know what my dissipated power is, I can use this electrical analog and say, here's my power I'm dissipating in my switch. I know these parameters. They're given to me on the data sheet. And I can then say, what's my temperature here? What's my junction temperature? I can define my case temperature. And you can look at every point along the way and determine temperature, which is the voltage across that node. So here's a quick example. And I'm sorry the graphics, the printing here got kind of goofed up. But what you're looking at is a voltage source, current sensing resistor, and this is the device we're interested in. This is a FET charging up a great big capacitor. Okay, so this is the basic circuit. Everything else here is just a control that limits the current here to, in this case, 10 amps. All right, so we start with the capacitor at 0, the input voltage at 12, and at T0 we connect them, and the FET is driven so that it limits the charging current here to 10 amps. So what you'll get is, so that's the electrical model. I took that and added, this is all in free LT Spice or P Spice, whatever you got. I took this device current, its drain voltage and its drain current right here, and said this is a dependent current source that takes that product. So in other words, this is power, right? This is power dissipated in this switch, and apply it to this thermal model. And I can then say, because I have the output shorted here, I'm saying that the final temperature is 0, meaning I'm looking at delta Tj, right? So if I look at here, this is going to be my delta, not time, it's delta Tj. And that's what I want to look at. So I run my simulation. So at T0, here's voltage, starts at 12 volts, ramps down to 0 as the capacitor bank charges. Current, I'm at 10 amps, so it's fixed at 10 amps until it's almost fully charged and then ramps down. Power dissipated, as you'd expect by multiplying these two, is also a ramp, and it is 120 watts peak, ramping down to 0 in about 14-15 milliseconds. And this is my predicted temperature rise. So temperature, it's not much at all. 0, it rises up to 18 or 19 degrees C, and then comes back down as the power is propagated through the device. So certainly no problem here in terms of delta Tj, which was easy to determine using the model I just showed you. I can further take the data that I just calculated in SPICE and plot it onto the SOA curve. So for example, at 1 millisecond, I'm still at 12 volts, I'm still at 10 amps, and here's my limit line. This is from the SOA curve, and I'm inside of that, so I'm safe here. Then I look at 10 milliseconds. My voltage has dropped quite a bit by this time. I'm now at, 3, 4 volts here, still at 10 amps because I'm still charging. And again, I'm within the SOA curve, right? And then at the end, at 14 milliseconds, I'm over here. So bottom line is, with a very simple simulation, I'm able to say, yes, in a fairly complex, not complex, but a non, it's not a square pulse, it's a rectangular pulse. I'm able to determine that I was able to stay within the SOA. A couple brief notes on operating FETs in parallel. If you look at the small signal equivalent model of a FET, you've got a couple of things to worry about here. You've got capacitances on the, this is gate, this is drain, this is source. Same thing here, gate, drain, source. I have some internal RG. I've got these nonlinear capacitances. I have a basically a current source is how this is modeled. And I've got parasitic wire bond inductance, maybe only a few nanohenries, but guess what? It makes a difference. And same thing on the drain here, drain and source, and my gate interconnect. And I'm driving it through this whole loop. What you'll find if you model this is that you can easily end up with an oscillator here just due to differences between the loop inductances. So one thing we always recommend is to not do this. You're better off using individual gate resistors here and here for each device. That helps to break that potential oscillatory loop. And I don't have time to go through the detail, but trust me on that one, okay? So what happens also is that on these two devices, let me just go back here, if this one has a lower gate threshold than this one, as I turn them on, this one's going to start to take current first, right? So this one's going to draw current before this one, and what happens is that as I begin to pick up, this is my total current here. I'm sorry, this is my gate voltage. First one picks up at threshold 1, so it takes all the current. Now the second one picks up, so it starts to take current, and here's my total. But every time you turn on, device 1 is going to be taking more current and therefore dissipating more power. All right, so what happens? It gets hotter, right? As it gets hotter, remember what I just showed you earlier? The threshold goes down even more, right? So now I'm down here. You can see what happens. You can end up with positive feedback where one device, because it has a low threshold, will take the hit and turn on before the other parallel devices. And so matching gate threshold is important. And my title here, the threshold can vary a lot from lot to lot. This just shows a kind of a distribution plot of different wafer lots. And so these are all within, so here's the specification here, 4 to 6.5 volts is what the datasheet says. And these are all well within that. But if I happen to take, this device and I get another tube, I'm assembling a bunch of these in parallel, and I have a device from here, I can have a very significant difference between them. So one of the things we always recommend is if you're paralleling a lot of devices at high current, at least take them all from a single wafer lot. That's the way that manufacturing orders them. I think we covered this. The threshold gets a lot worse with delta T. However, statically, because of this, curve we looked at earlier, the dynamic, so the switching characteristics get worse as temperature differences become worse. However, conduction losses tend to even out because of the positive temperature coefficient of RDS on. Okay. Also, avalanche. When you have devices in parallel and they avalanche, this is a test where we took 4 devices, the 4 different colors here. We turned them on. You can see them taking current. So this is current ramping up in all 4 of them. This is an unclamped inductor. Then we shut off all 4 switches and see how do they share avalanche current as they ramp back down. So you can see that devices with, this one had the lowest avalanche threshold, this had the highest. So there's a fair amount of disparity. But then if I then allow one to get even hotter, you can see even larger differences. So again, the same kind of issues sharing during avalanche characteristic. So in summary on the FETs, don't assume that everything's going to share equally. Static mismatches will tend to even out, but dynamic mismatches depend strongly on gate threshold and the symmetrical layout. Use the individual gate resistors on each gate. Avalanche temperature coefficient does promote sharing, but again, it depends on how fast it is and if the temperature gets time to equalize or not. Just very quickly, I have 1 or 2 minutes left here. Talk about gallium nitride. This is a new technology that, well, it's actually not new. It's been around for a while in RF, but for power, it's relatively new. And you'll see more about this coming up. These are lateral devices where the source and drain and gate are all on one side, which creates some unique possibilities. You can make symmetrically blocking devices, or you can optimize them for unidirectional. They're normally on devices intrinsically. There are some tricks you can do to make them normally off. But what you'll see first in the market is what's called a cast-coated device, where this is the GaN, and this is a low voltage silicon FET. So essentially the GaN is sitting on top of the silicon device, and it extends the voltage range. So this is let's say a 20 volt silicon switch. It now becomes a 600 volt silicon switch with very high performance by adding the GaN. It's called a high electron mobility transistor, a HEMT, on top of that. And you can drive it with standard gate drive. So this behaves like a normal FET, but has much higher performance. And I guess we're out of time here. So summarize, FETs are application specific. Again, just like with the IGBTs, there are trade-offs in speed and conductivity and breakdown voltage. The data sheets, they tend to show you the idealized theoretical upper limits, so don't always believe those numbers that are actually achievable. Real world capability is somewhere in the middle. Always pay attention to safe operating area, and normally you're not spending a lot of time in the middle of it, but for linear mode applications you are. FETs can certainly be operated in parallel successfully as long as you follow the rules I mentioned and derate them for the times when they don't share equally. And you'll be seeing a lot more on silicon carbide MOSFETs and even bipolar BJTs out of silicon carbide up to about 1200 volts. GaN is probably going to be in the 100 to 700 volt range for now, for the foreseeable future. I don't know that it's going to make it to 1200 anytime soon, but we'll see. Okay, so I went over. I'll stick around for questions if you need.
Around